Okay, we're now at Chapter 19, Advanced Features. By now you've learned the most commonly used parts of Rust programming language. Before we do one more project in Chapter 20, we'll look at a few aspects of the language you might run into every once in a while. You can use this chapter as a reference for when you encounter any unknowns when using Rust. The features you'll learn to use in this chapter are useful in very specific situations. Although you might not reach for them often, we want to make sure you have a grasp of all the features Rust has to offer. In this chapter, we'll cover Unsafe Rust, how to opt out of some of Rust's guarantees and take responsibility for manually upholding those guarantees. Advanced traits, associated types, default type parameters, fully qualified syntax, super traits, and the new type pattern in relation to traits. Advanced types, more about the new type pattern, type aliases, the never type, the dynamically sized types, advanced functions and closures, function pointers and returning closures, macros, ways to define code that defines more code at compile time. It's a panoply of Rust features with something for everyone. Let's dive in. Unsafe Rust. All of the code we've discussed so far has Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called Unsafe Rust and works just like regular Rust but gives us extra superpowers. Unsafe Rust exists because by nature static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some value programs rather than accept some invalid programs. Although the code might be okay as far as Rust is able to tell, it's not. In these cases, you can use unsafe code to tell the compiler, "Trust me, I know what I'm doing." Famous last words, huh? The downside is that you use it at your own risk. If you use unsafe code incorrectly, problems due to memory unsafety, such as null pointer differencing can occur. Another reason Rust has an unsafe alter ego is that the underlying computer hardware is inherently unsafe. If Rust didn't let you do unsafe operations, you couldn't do certain tasks. Rust needs to allow you to do low-level systems programming, such as directly interacting with the operating system or even writing your own operating system. Working with low-level systems programming is one of the goals of this language. Let's explore what we can do with Unsafe Rust and how to do it. Unsafe Superpowers. To switch to Unsafe Rust, use the unsafe keyword and then start a new block that holds the unsafe code. You can take 4 actions in Unsafe Rust called Unsafe Superpowers that you can't in Safe Rust. Those superpowers include the ability to deference a raw pointer, call an unsafe function or method, access or modify a mutable static variable, implement an unsafe trait, and access fields of Union S. It's important to understand that unsafe doesn't turn off the borrow checker or disable any other Rust safety checks. If you use a reference in unsafe code, it will let's see, it will still be checked. The unsafe keyword only gives you access to these 4 features that are then not checked at, let's see, by the compiler for memory safety. You'll still get some degree of safety inside of an unsafe block. In addition, unsafe does not mean the code inside the block is necessarily dangerous, or that it will definitely have memory safety problems. The intent is that as the programmer, you'll ensure that the code inside the unsafe block will access memory in a valid way. People are fallible and mistakes will happen, but requiring these 4 unsafe operations to be inside block annotations with unsafe, you'll know that any errors related to memory safety must be within the unsafe block. Keep unsafe blocks small. You'll be thankful later when you investigate memory bugs. To isolate unsafe code as much as possible, it's best to enclose unsafe code within the safe abstraction and provide a safe API, which we'll discuss later in the chapter when we examine unsafe functions and methods. Parts of the standard library are implemented as safe abstractions over unsafe code that has been audited. Wrapping unsafe code in a safe abstraction prevents use of unsafe from leaking out into all the places that you or your user might want to use the functionality implemented with unsafe code, because using a safe abstraction is safe. Let's look at each of the 4 unsafe superpowers in turn. We'll also look at some abstractions that provide a safe interface to Unsafe code. Deferencing a raw pointer. Just in case any of you are wondering, that is just the noise of my chair when I go into recline motion. Okay. Deferencing a raw pointer. In Chapter 4, in the Dangling References section, we mentioned that the compiler ensures references are always valid. Unsafe Rust has 2 new types called raw pointers that are similar to references. As with references, raw pointers can be immutable or mutable and are written as, let's see, what do they call that again? Asterisk. Okay, asterisk, I guess. Const for construct, T, and asterisk mute T, respectively. The asterisk isn't the deference operator. It's part of the type name in the context of raw pointers. Immutable means that the pointer can't be directly assigned to after being dereferenced. Different from references and smart pointers, raw pointers are allowed to ignore the borrowing rules and have both immutable and mutable pointers, or mutable or multiple mutable pointers to the same location. Aren't guaranteed to point to valid memory, are allowed to be null, and don't implement any automatic cleanup. By opting out of having Rust enforce these guarantees, you can give up guaranteed safety in exchange for greater performance, or the ability to interface with other languages or hardware where Rust guarantees don't apply. Listing 19-1 shows how to create an immutable and a mutable raw pointer from references. Listing 19-1, creating raw pointers from references. Notice that we don't include the unsafe keyword in this code. We can create raw pointers in safe code. We just can't deference raw pointers outside the unsafe block, as you'll see in a bit. We've created raw pointers by using as to cast an immutable and a mutable reference into their corresponding raw pointer types. Because we created them directly from references guaranteed to be valid, we know these particular raw pointers are valid. But we can't make that assumption about just any raw pointer. Next, we'll create a raw pointer whose validity we can't be so certain of. Listing 19-2 shows how to create a raw pointer to an arbitrary location in memory. Trying to use arbitrator memory is undefined. There might be data at the address, or there might not. The compiler might optimize the code so that there is no memory access, or the program might error with a segment fault. Usually there's no good reason to write code like this, but it's possible. Listing 19-2, creating a raw pointer to an arbitrary memory address. Recall that we can create raw pointers in safe code, but we can't deference raw pointers and read the data being pointed to. In listing 19-3, we use the difference operator, which is the asterisk, on the raw pointer that requires an unsafe block. Listing 19-3, deferencing raw pointers within an unsafe block. Creating a pointer does no harm. It's only when we try to access the value that it points at that we might end up dealing with an invalid value. Note also that in listing 19-1 and 19-3 we created asterisk const I32 and asterisk mute I32 raw pointers that both pointed to the same memory location where the num is stored. If we instead tried to create an immutable and mutable reference to num, the code would not have compiled because Rust immutable and a mutable reference to num. Let's see, if we instead tried to create an immutable and a mutable reference to num, the code would not have compiled because Rust ownership rules don't allow mutable reference at the same time as an immutable references with raw pointers. We can create a mutable pointer and an immutable pointer to the same location and change data through the mutable pointer, potentially creating a data race. Be careful. With all these dangers, why would you ever want to use raw pointers? One major use case is when interfacing with C code. As you'll see in the next section, calling an unsafe function or method. Another case is when building up safe abstractions that the borrow checker doesn't understand. We'll introduce unsafe functions and then look at an example of a safe abstraction that uses unsafe code. Calling an unsafe function or method. The second type of operation that requires an unsafe block is calls to unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements that we need to uphold when we call this function, because Rust can't guarantee we've met these requirements. By calling an unsafe function with an unsafe block, we're saying that we've read this function's documentation and take responsibility for upholding the function's contracts. Here is an unsafe function named dangerous that doesn't do anything in its body. We must call the dangerous function within a separate unsafe block. If we try to call dangerous without the unsafe block, we'll get an error. By inserting the unsafe block around our call to dangerous, we're asserting to Rust that we've read the function's documentation, we understand how to use it properly, and we've verified that we're fulfilling the contract of the function. Bodies of unsafe functions are effectively unsafe blocks. So, to perform other unsafe operations within an unsafe function, we don't need to add another unsafe block. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark an entire function as unsafe. In fact, wrapping unsafe code in a safe function is a common abstraction. As an example, let's study a function from the standard library, split_at_mute, that requires some unsafe code and explore how we might implement it. This safe method is defined on mutable slices. It takes one slice and makes two by splitting the slice at the index given as an argument. Listing 19-4 shows how to use split_at_mute. Listing 19-4 using the safe split_at_mute function. We can't implement this function using only safe Rust. An attempt might look something like listing 19-5, which won't compile. For simplicity, we'll implement split_at_mute as a function rather than a method, and only for slices of I32 values rather than a generic type T. Listing 19-5, an attempted implementation of split_at_mute using only safe Rust. This function first gets the total length of the slice. Then it asserts that the index given as a parameter is within the slice by checking whether it's less than or equal to the length. The assertion means that if we pass the index that is greater than the length to split the slice at, the function will panic before it attempts to use that index. Then we return two mutable slices in a tuple, one from the start of the original slice to the mid index and another from mid to the end of the slice. We'll try to compile the code in listing 19-5. We'll get an error. Rust's borrow checker can't understand that we're borrowing different parts of the slice. It only knows that we're borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay because the two slices aren't overlapping, but Rust isn't smart enough to know this. When we know code is okay, but Rust doesn't, it's time to reach for unsafe code. Listing 19-6 shows how to use an unsafe block, a raw pointer, and some calls to unsafe functions to make the implementation of split_at_mute work. Listing 19-6 using unsafe code in the implementation of the split_at_mute function. Recall from the slice type section in Chapter 4 that slices are a pointer to some data and the length of the slice. We use the len method to get the length of a slice and the as underscore mute underscore print ptr method to assert the raw pointer of a slice. In this case, because we have a mutable slice to I32 values, as underscore mute underscore ptr returns a raw pointer. Okay, I'm guessing ptr stands for pointer with the type asterisk mute I32, which we've stored in the variable pointer. We keep the assertion that the mid index is within the slice. Then we get the unsafe code. Then we get to the unsafe code. The slice : from underscore raw underscore parts underscore mute function takes the raw pointer and a length, and it creates a slice. We use this function to create a slice that starts from pointer and is mid items long. Then we call the offset method on pointer with mid as an argument to get raw pointer that starts at mid, and we create a slice using that pointer and the remaining number of items after mid as the length. This function, slice : from underscore raw underscore parts underscore mute, is unsafe because it takes a raw pointer and must trust that this pointer is valid. The offset method on raw pointers are also unsafe because it must trust that the offset location is also a valid pointer. Therefore, we had to put an unsafe block around our calls to slice : from underscore raw underscore parts underscore mute and offset, so we could call them. By looking at the code and by adding the assertion that mid must be less or equal to length, we can tell that all the raw pointers used within the unsafe block will be valid pointers to data within the slice. This is an acceptable and appropriate use of unsafe. Note that we don't need to mark the resulting split underscore at underscore mute function as unsafe, and we can call this function from Safe Rust. We've created a safe abstraction to an unsafe code with an implementation of the function that uses unsafe code in a safe way. Because it creates only valid pointers from the data this function has to access. In contrast, the use of the slice : from underscore raw underscore parts underscore mute in listing 19-7 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice 10,000 items long. Listing 19-7, creating a slice from an arbitrary memory location. We don't own the memory at this arbitrary location, and there is no guarantee that the slice this code creates contains a valid I32 values. Attempting to use slice as though it's a valid slice results in undefined behavior. Using extern functions to call external code. Sometimes your Rust code might need to interact with code written in another language. For this, Rust has a keyword, extern, that facilitates the creation of use of a foreign function interface, FFI. And FFI is a way for a programming language to define functions and enable a different foreign programming language to call those functions. Listing 19-8 demonstrates how to set up integration with the ABS function from the C standard library. Functions declared within external blocks are always unsafe to call from Rust code. The reason is that other languages don't enforce Rust rules and guarantees, and Rust can't check them. So responsibility falls on the programmer to ensure safety. Listing 19-8, declaring and calling an external function defined in another language. Within the external C block, we list the names and signatures of external functions from another language we want to call. The C part defines which application binary interface ABI the external function uses. The ABI defines how to call function at the assembly level. The C ABI is the most common and follows the C programming language ABI. Calling Rust functions from other languages. We can also use the external to create an interface that allows other languages to call Rust functions instead of an external block. We add the external keyword to specify the ABI to use it just before the function keyword. We also need to add a hashtag close bracket no underscore mango close bracket annotation to tell the Rust compiler not to mangle the name of this function. Mangling is when a compiler changes the name we've given a function to a different name that contains more information for other parts of the compilation process to consume, but in less human readable. Process to consume, but is less human readable. Okay. Every programming language compiler mangles names slightly differently. So for a Rust function to be nameable by other languages, it must disable the Rust compiler's name mangling. In the following example, we make the call from C function accessible from C code after it's compiled to a shared library and linked from C. This usage of external does not require unsafe. Accessing or modifying a mutable static variable. Until we've not talked about global variables, which Rust does support but can be problematic with Rust ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. In Rust, global variables are called static variables. And listing 19-9 shows an example declaration and use of a static variable with a string slice as a value. Listing 19-9 defining and using an immutable static variable. Static variables are similar to constants, which we discussed in the differences between variables and constants section in Chapter 3. The names of static variables are in screaming _snake _case by convention, and we must annotate the variable's type, which is in reference single quote static string. In this example, static variables can only store references with the single. Now I guess that's going to be a let me look for it here. And let's let's see, I'm guessing it's just an apostrophe. Apostrophe static, or single quote, I don't know. Let me see if the double quote is going to be called a double quote. And yeah, well, it must be considered a single quote mark. Okay. Static variables are similar to constants, which we've discussed in the differences between variables and constants in section chapter 3. Let's see, the name of static variables are in the screaming underscore snake underscore case by convention. And we must annotate the variable's type, which is reference, single quote, static, string. In this example, static. Variables can only store references with the single quote static lifetime, which means the Rust compiler can figure out the lifetime. We don't need to annotate it explicitly. Accessing an immutable static variable is safe. Constants and immutable static variables might seem similar, but a subtle difference is the values in a static variable have a fixed address in memory. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they're used. Another difference between constants and static variables is that static variables can be mutable. Accessing and modifying mutable static variables is unsafe. Listing 19-10 shows how to declare, access, and modify a mutable static variable named counter. Listing 19-10, reading from or writing to a mutable static variable is unsafe. As with regular variables, we must specify mutability using the mute keyword. Any code that reads or writes from counter must be within an unsafe block. This code compiles and prints counter: 3, as we would expect, because it's single-threaded. Okay, because it's single-threaded. Having multiple threads access counter would likely result in data races. With mutable data that is globally accessible, it's difficult to ensure that there are no data races, which is why Rust considers mutable static variables to be unsafe. Where possible, it's preferable to use concurrency techniques and thread-safe smart pointers we've discussed in Chapter 16, so the compiler checks that data accessed from different threads is done safely. Implementing an unsafe trait. The final action that works only with unsafe is implementing an unsafe trait. A trait is unsafe when at least one of its methods has some variant that the compiler can't verify. We can declare that a trait is unsafe by adding the unsafe keyword before trait and marking the implementation of the trait as unsafe too, as shown in listing 19-11. Listing 19-11, defining and implementing an unsafe trait. By using unsafe implementation, we're promising that we'll uphold the invariance that the compiler can't verify. An example, recall the sync and send marker traits that we discussed in the extendable concurrency with the sync and send traits section in Chapter 16. The compiler implements these traits automatically if our types are composed entirely of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, and we want to mark that type as send or sync, we must use unsafe. Rust can't verify that our type upholds the guarantee that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do those checks manually and indicate as such with unsafe. When to use unsafe code. Using unsafe to take one of the four actions, superpowers, just discussed isn't wrong or even frowned upon, but it is trickier to get unsafe code correct because the compiler can't help uphold memory safety. When you have a reason to use unsafe code, you can do so, and having the explicit unsafe annotation makes it easier to track down the source of your problems if they do occur. Okay. Advanced traits. We'll first cover traits in the Traits Defining Shared Behavior section of Chapter 10. We first covered traits in the Traits Defining Shared Behavior section of Chapter 10, but as with lifetimes, we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty-gritty. Specifying placeholder types in trait definitions with associated types. Associated types connect a type placeholder with a trait such that the trait method definitions can use these placeholder types in their signatures. The implementer of a trait will specify the concrete type to be used in this type's place for a particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. We've described most of the advanced features in this chapter as being rarely needed. Associated types are somewhere in the middle. They're used more rarely than features explained in the rest of the book, but more commonly than many of the other features discussed in this chapter. One example of a trait with an associated type is the integer trait that the standard library provides. The associated type is named item and stands in for the type of the values the type implementing the integrator trait is iterating over. In the iterator trait and the next method section of chapter 13, we mentioned that the definition of the iterator trait is as shown in listing 19-12. Listing 19-12, the definition of the iterator trait that has an associated type item. The type item is a placeholder type, and the next method definition shows that it will return values of type option less than self : item greater than. Implementers of the iterator trait will specify with concrete type for item. And the next method will return an option containing a value of that concrete type. Associated types might seem like a similar concept to generics, in that the latter allow us to define a function without specifying what types it can handle. So why use associator types? Let's examine the difference between the two concepts with the example from Chapter 13 that implements the iterator trait on the counter struct. In listing 13-21, we specified that the item type was U32. This syntax seems comparable to that of generics, so why not just define the iterator trait with generics as shown in listing 19-13? Listing 19-13, a hypothetical definition of the iterator trait using generics. The difference is that when using generics, as in listing 19-13, we must annotate the type in each implementation, because we can also implement iterator, less than string greater than for counter, or any other type. We could have multiple implementations of iterator for counter. Iterator. In other words, when a trait has a generic perimeter, it can be implemented for a type multiple times, changing the concrete types of the generic type perimeters each time. Then, when we use the next method on a counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associator types, we don't need to annotate types because we can't implement a trait on a type multiple times. In listing 19-12, with the definition that uses associated types, we can only choose what the type of item will be once, because there can only be one implementation iterator for counter. We don't have to specify what we want iterator of U32 values anywhere that we call next on counter. Default generic type parameters and operator overloading. When we use generic type parameters, we can specify a default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type if the default type works. The syntax for specifying a default type for generic type is less than placeholder type equal concrete type greater than when declaring a generic type. A great example of a situation where this technique is useful is with operator overloading. Operator overloading is customizing the behavior of an operator such as plus sign. In particular situations, Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations and corresponding traits listed in standard library : ops by implementing the traits associated with the operators. For example, in listing 19-14, we overload the plus operator to add 2 point instances together. We do this by implementing the add trait on a point struct. Listing 19-14, implementing the add trait to overload the plus operator for point instances. The add method adds the x values of 2 point instances and the y values of 2 point instances to create a new point. The add trait has an associated type named output that determines the type returned from the add method. The default generic type in this code is within the add trait. Here is its definition. This code should look generally familiar, a trait with one method and an associated type. The new part is RHS equals self. This syntax is called default type parameters. The RHS generic type parameter, shorthand for right hand side, defines the type of the right hand side parameter in the add method. If we don't specify a concrete type for right hand side, when we implement the add trait, the type of the right hand side will default to self, which will be the type we're implementing add on. When we implement add for point, we use the default for right hand side because we want to add 2 point instances. Let's look at an example of implementing the add trait where we want to customize the right hand side type rather than using the default. We have two structs, millimeters and meters, holding values in different units. We want to add values in millimeters to values in meters and have the implementation of add do the conversion correctly. We can implement add for the millimeters with meters as right hand side, as shown in listing 19-5, 19-15. Listing 19-15, implementing the add trait on millimeters to add meters to millimeters to meters. To add millimeters and meters, we specify the implementation add less than meters greater than to set the value of the right hand side type parameter instead of using the default of self. You'll use default type parameters in two main ways: to extend a type without breaking existing code, to allow customization in specific case most users won't need. The standard library's add trait is an example of the second purpose. Usually you'll add two like types, but the add trait provides the ability to customize beyond that. Using the default type parameter in the add trait definition means you don't have to specify the extra parameter most of the time. In other words, a bit of implementation boilerplate isn't needed, making it easier to use the trait. The first purpose is similar to the second, but in reverse. If you want to add a type parameter to an existing trait, you can give it a default. You can give it a default to allow extension of the functionality of the trait without breaking an existing implementation code. Fully qualified syntax for disambiguation, calling methods with the same name. Nothing in Rust prevents a trait from having a method with the same name as another trait's method, nor does Rust prevent you from implementing both traits on one type. It's also possible to implement a method directly on the type with the same name as methods from traits. When calling methods with the same name, you'll need to tell Rust which one you want to use. Consider the code in listing 19-16, where we've defined two traits, pilot and wizard, that both have a method call fly. When we implement both traits on a type human that already has a method named fly implemented on it, each fly method does something different. Listing 19-16, two traits are defined to have a fly method and are implemented on the human type, and the fly method is implemented on human directly. When we call fly on an instance of human, the compiler defaults to calling the method that is directly implemented on the type, as shown in listing 19-17. Listing 19-17 calling fly on an instance of human. Running this code will print asterisk waving arms furiously asterisk, showing that Rust called the fly method implemented on human directly. To call the fly method from either the pilot trait or the wizard trait, we need to use more explicit syntax to specify which fly method we mean. Listing 19-18 demonstrates this syntax. Listing 19-18 specifying which trait fly method we want to call. Specifically, the trait name before the method name clarifies to Rust which implementation of fly we want to call. We could also write human : fly parenthesis reference person parenthesis, which is equivalent to the person.fly parenthesis that we used in listing 19-18, but this is a bit longer to write if we don't need to disambiguate. Running this code prints the following. Because the fly method takes a self parameter, if we had two types that both implement one trait, Rust could figure out which implementation of trait to use based on the type of self. However, associated functions that are part of a trait don't have a self parameter. When two types in the same scope implement that trait, Rust can't figure out which type you mean unless you use fully qualified syntax. For example, the animal trait in listing 19-19 has the associated function baby_name. The implementation of animal for the struct dog, and the associated function baby_name defined on dog directly. Listing 19-19, a trait with an associated function and a type with an associated function of the same name that also implements the trait. This code is for an animal shelter that wants to name all puppies. Slot, puppies, name all puppies. Spot, which is implemented in baby_name, associated function that is defined on dog. The dog type also implements the trait animal, which describes characteristics that all animals have. Baby dogs are called puppies, and that is expressed in the implementation of the animal trait on dog in the baby_name function associated with the animal trait. In main, we call the dog : baby_name function, which calls the associated function defined on dog directly. This code prints the following code. This output isn't what we wanted. We wanted to call the baby_name function that is part of the animal trait that we implemented on dog. So the code prints a baby dog is called a puppy. The technique of specifying the trait name that we used in listing 19-18 doesn't help here. If we change main to the code in listing 19-20, we'll get a compilation error. Listing 19-20, attempting to call the baby underscore name function from the animal trait, but Rust doesn't know which implementation to use. Because animal : baby underscore name is an associated function rather than a method, and thus doesn't have a self parameter, Rust can't figure out which implementation of animal : baby underscore name we want. You see, we'll get this compiler error. To disambiguate and tell Rust that we want to use the implementation of animal for dog, we need to use fully qualified syntax. Listing 19-21 demonstrates how to use fully qualified syntax. Listing 19-21, using fully qualified syntax to specify that we want to call the baby underscore name function from the animal trait as implemented on dog. We're providing Rust with a type annotation within the angle brackets, which indicates that we want to call the baby underscore name method from the animal trait as implemented on dog by saying that we want to treat the dog type as an animal for this function call. This code will now print what we want. In general, fully qualified syntax is defined as follows. For associated functions, there would not be a receiver. There would only be a list of other arguments. You could use fully qualified syntax anywhere that you call functions or methods. However, you're allowed to omit any part of this syntax that Rust can figure out from other information in the program. You only need to use this more verbose syntax in cases where there are multiple implementations that use the same name, and Rust needs help to identify which implementation you want to call. Using super traits to require one trait's functionality with another trait. Sometimes you might need one trait to use another trait's functionality. In this case, you need to rely on the dependent trait also being implemented. The trait you rely on is a supertrait of the trait you're implementing. For example, let's say we want to make an outline print trait with an outline underscore print method that will print a value framed in asterisks. That is, given a point struct that implements display to result in X and Y. Then we call outline underscore print on the point instance that has 1 for X and 3 for Y. It should print the following. In the implementation of the outline underscore print, we want to use the display traits functionality. Therefore, we need to specify that the outline print trait will work only for types that also implement display and provide the functionality that outline print needs. We can do that in the trait definition by specifying outline print : display. This technique is similar to adding a trait bound to the trait. Listing 19-22 shows an implementation of the outline print trait. Listing 19-22, implementing the outline print trait that requires the functionality from display. Because we've specified that outline print requires the display trait, we can use the to_string function that is automatically implemented for any type that implements display. If we try to use to underscore string without adding a colon and specifying the display trait after the trait name, we'd get an error saying that no method named to underscore string was found for the type reference self in the current scope. Let's see what happens when we try to implement outline print on a type that doesn't implement display, such as the point struct. We get an error saying that display is required but not implemented. To fix this, we implement display on point and satisfy the constraint that outline print requires, like so. Then implementing the outline print trait on point will compile successfully, and we can call outline underscore print on a point instance to display it within the outline of asterisks. Using the new type pattern to implement external traits on external types. In Chapter 10, in the implementing a trait on a type section, we mentioned the orphan rule that states were allowed to implement a trait on a type as long as either the trait or the type are local to our crate. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple struct. We covered tuple structs in the Using Tuple Structs without named fields to create different types section of Chapter 5. The tuple struct will have one field and be in a thin wrapper around the type we want to implement for. Let's implement a trait for. Then the wrapper type is local to our crate, and we can implement the trait on the wrapper. New type is a term that originates from the Haskell programming language. There is no runtime performance penalty for using this pattern, and the wrapper type is allied at compile time. Okay, as an example, let's say we want to implement display on vector t, which the orphan rule prevents us from doing directly because the display trait and the vector t type are defined outside of our crate. We can make a wrapper struct that holds an instance of vertical t. Then we can implement display on wrapper and use the vector t value as shown in listing 19-23. Listing 19-23, creating a wrapper type around vecstring to implement display. The implementation of display uses self.0 to access the inner vector t. Because wrapper is a tuple struct and vector t is the item at index 0 in the tuple. Then we can use the functionality of the display type on wrapper. The downside of using this technique is that wrapper is a new type, so it doesn't have the methods of the value it's holding. We would have to implement all the methods of vector t directly on wrapper, such that the methods delegate to self.0, which would allow us to treat wrapper exactly like a vector t. If we wanted the new type to have every method the inner type has, implementing the deference dereference trait discussed in Chapter 15 in the treating smart pointers like regular references with the deference trait section. on the wrapper to return the inner type would be a solution. If we didn't want the wrapper type to have all of the methods of the inner type, for example, to restrict the wrapper type's behavior, we would have to implement just the methods we do want manually. Now you know how the new type pattern is used in relation to traits. It's also a useful pattern even when traits are not involved. Let's switch focus and look at some advanced ways to interact with Rust's type system. Advanced types. The Rust type system has some features that we've mentioned in this book but haven't yet discussed. We'll start by discussing new types in general as we example why new types are useful as types. Then we'll move on to type aliases, a feature similar to new types but with slightly different semantics. We'll also discuss the exclamation mark type and dynamic sized types. Note, in this section, the next section assumes you've read the earlier section using the new type pattern to implement external traits on external types. using the new type pattern for type safety and abstraction. The new type pattern is useful for tasks beyond those we've discussed so far, including statically enforcing that values are never confused and indicating the units of value. You saw an example of using new types to indicate units in listing 19-15. Recall that millimeters and meter structs wrapped in U32 values in a new type. If we wrote a function with a parameter of type millimeters, we couldn't compile a program that accidentally tried to call that function with a value of type meters or a plain U32. Another use of the new type pattern is in abstracting away some implementation details of a type. The new type can expose a public API that is different from the API of the private inner type if we use the new type directly to restrict the available functionality, for example. New types can also hide internal implementation. For example, we could provide a people type to wrap a hash map less than I32, string greater than that stores a person's ID associated with their name. Code using people would only interact with the public API we provide. Such a method to add a name string to the people collection. That code wouldn't need to know that we assign an I32 ID to names internally. The new type pattern is a lightweight way to achieve encapsulation to hide implementation details, which we discussed in the encapsulation that hides implementation details section of chapter 17. Creating type synonyms, there's another word that's hard to pronounce, synonyms with type aliases. Along with the new type pattern, Rust provides the ability to declare a type alias to give an existing type another name. For this, we use the type keyword. For example, we can create the alias kilometers to I32 like so. Now, the alias kilometers is a synonym for I32. Unlike the millimeters and meters type meters type we created in listing 19-15. Kilometers is not a separate new type. Values that have the type kilometers will be treated the same as value of type I32. Because kilometers and I32 are the same type, we can add values of both types, and we can pass kilometer values to functions that take I32 parameters. However, using this method, we don't get the type checking benefit that we get from the new type pattern discussed earlier. The main use case for type synonyms is to reduce repetition. For example, we might have a lengthy type like this. Writing this lengthy type of function signatures as type annotations all over the code can be tiresome and error-prone. Imagine having a project full of code like that in listing 19-24. Listing 19-24 using a long type in many places. A type alias makes this code more manageable by reducing the repetition. In listing 19-25, we've introduced an alias named Thunk for the verbose type that can replace all uses of the type with the shorter alias Thunk. Listing 19-25, introducing a type alias Thunk to reduce repetition. This code is much easier to read and write. Choosing a meaningful name for the type alias can help communicate your intent as well. Thunk is a word for code to be evaluated at a later time. So it's an appropriate name for a closure that gets stored. Type aliases are also commonly used with the result TE type for reducing repetition. Consider the standard library : in out module in the standard library. I/O operations often return a result TE to handle situations when operations fail to work. This library has a standard : in out : error struct that represents all possible I/O errors. Many of the functions in standard library : in out will be returning result TE, where the E is standard library : in out : errors, such as these functions in the write trait. The result less than ... error greater than is repeated a lot. As such, standard library : in out has this type of alias declaration. Because this declaration is in the standard library : in out module, we can use the fully qualified alias standard library : in out : result T. That is a result TE with the E filled in as standard library : in out : error. The write trait function signatures end up looking like this. The type alias helps in two ways. It makes the code easier to write and gives it a consistent interface across all standard library : in out. Because it's an alias, it's just another result TE, which means we can use any method that works on result TE with it, as well as special syntax like the question mark operator. The never type that never returns. Rust has a special type named exclamation mark that is known in type theory lingo as the empty type because it has no values. We prefer to call it the never type because it stands in place of the return type when a function will never return. Here's an example. This code is read as the function bar returns never. Functions that return never are called diverging functions. We can't create values of the type exclamation mark, so bar can never possibly return. But what use is a type you can never create values for. Recall the code from listing 2-5. We've reproduced that part of it here in listing 19-26. Listing 19-26, a match with an arm that ends in continue. At the time, we skipped over some details in this code. In Chapter 6, in the match control flow operator section, we discussed that match arms must all return the same type. So, for example, the following code doesn't work. The type of guess in this code would have to be an integer and a string, and Rust requires that guess have only one type. So what does continue return? How were we allowed to return a U32 from one arm and have another arm that ends with continue in listing 19-26? As you might have guessed, continue has a exclamation value. That is, when Rust computes the type of guess, it looks at both match arms, the former with a value of U32 and the latter with an exclamation mark value. Because exclamation mark can never have a value, Rust decides that type of guess is U32. The formal way of describing this behavior is that expressions of type exclamation mark can be coerced into any other type. We're allowed to end this match arm with continue because continue doesn't return a value. Instead, it moves control back to the top of the loop, so the error case, we never assigned value to guess. The never type is useful with the panic exclamation mark macro as well. Remember the unwrap function that we call an option T values to produce a value or panic. Here is its definition. In this code, the same thing happens as in the match in listing 19-26. Rust sees that val value has the type T and panic exclamation mark has the type exclamation mark. So the result of the overall match expression is T. This code works because panic exclamation mark doesn't produce a value. It ends the program. In the none case, we won't be returning a value from unwrap, so this code is valid. One final expression that has the type exclamation mark is a loop. Here, the loop never ends, so exclamation mark is the value of the expression. However, this wouldn't be true if we included a break because the loop would terminate when it got to the break. Dynamically sized types and the sized trait. Due to Rust's need to know certain details such as how much space to allocate for a value of a particular size, there is a corner of its type system that can be confusing, the concept of dynamically sized types, sometimes referred to as DSTs, or unsized types. These types let us write code using values whose size we can only know at runtime. Let's dig into the details of dynamically sized type called string, which we've been using throughout the book. That's right, not reference string, but string on its own, is a DST. We can't know how long the string is until runtime, meaning we can't create a variable of type string, nor can we take an argument of type string. Consider the following code, which does not work. Rust needs to know how much memory to allocate for the values of a particular type, and the values of the type must use the same amount of memory. If Rust allowed us to write this code, these two string values would need to take up the same amount of space, but they have different lengths. S1 needs 12 bytes of storage and S2 needs 15. This is why it's not possible to create a variable holding a dynamic size type. So what do we do? In this case, you already know the answer. We make the types of string 1 and string 2 a reference string rather than a string. Recall that in the string slices section of chapter 4, we said the slice data structure stores the starting position and the length of the slice. So although a reference T is a single value that stores the memory address of where the T is located, a reference string is two values, the address of the string and its length. As such, we can know the size of a reference string value at compile time. It's twice the length of a use size. That is, we always know the size of a reference string no matter how long the string it refers to is. In general, this is the way in which dynamically sized types are used in Rust. They have an extra bit of metadata that stores the size of the dynamic information. The golden rule of dynamically sized types is that we must always put values of dynamically sized types behind a pointer of some kind. We can combine string with all kinds of pointers, for example, box string or RC string, reference count. In fact, you've seen this before, but with a different dynamic size type, traits. Every trait is a dynamically sized type we can refer to by using the name of the trait. In Chapter 17, in the Using Trait Objects that Allow for Values of Different Types section, we mentioned that to use traits as trait objects, we must put them behind a pointer, such as reference dynamic trait or box dynamic trait or reference count dynamic trait would work too. To work with DSTs, Rust has a particular trait called size trait to determine whether or not a type size is known at compile time. This trait is automatically implemented for everything whose size is known at compile time. In addition, Rust implicitly adds a bound on size to every generic function. That is, a generic function definition like this is actually treated as though we had written this. By default, generic functions will work only on types that have a known size at compile time. However, you can use the following special syntax to relax this restriction. A trait bound on $size is the opposite of a trait bound on size. We would read this as T may or may not be sized. This syntax is only available for sized, not any other traits. Also note that we switched the type of the T parameter from T to reference T because the type might not be sized. We need to use it behind some kind of pointer. In this case, we've chosen a reference. Next, we'll talk about functions and closures. Advanced Functions and Closures. Finally, we'll explore some advanced features related to functions and closures, which include function pointers and returning closures. Function pointers. We've talked about how to pass closures to functions. You can also pass regular functions to functions. This technique is useful when you want to pass a function you've already defined rather than defining a new closure. Doing this with function pointers will allow you to use functions as arguments to other functions. Functions coerce to this type function with the lowercase f, not to be confused with the function closure trait. The function trait or type is called a function pointer. The syntax for specifying that parameter is a function pointer The syntax for specifying that a parameter is a function pointer is similar to that of closures, as shown in listing 19-27. Listing 19-27 using a function type to accept a function pointer as an argument. This code prints the answer is :12. We specify that the parameter f in do underscore twice is an function that takes one parameter of type I32 and returns an I32. We can then call f in the body of do underscore twice in main. We can pass the function name add underscore 1 as the first argument to do underscore twice. Unlike closures, function is a type rather than a trait, so we specify function as the parameter type directly rather than declaring a generic type parameter with one of the function traits as a trait bound. Function pointers implement all three of the closure traits: function, function mute, and function once. So you can always pass a function pointer as an argument for a function that expects a closure. It's best to write functions using a generic type and one of the closure traits so that your function can accept either functions or closures. An example of where you would want to only specify function and not closures is when interlacing with external code that doesn't have closures. C functions can accept functions as arguments, but C doesn't have closures. An example of where you could use either a closure defined inline or a named function, let's look as an example of where you could use either a closure defined inline or a named function. Let's look at a use of map. To use the map function to turn a vector of numbers into a vector of strings, we could use a closure like this. Or we could name a function as the argument to map instead of the closure like this. Note that we must use the fully qualified syntax that we talked about earlier in the advanced traits section because there are multiple functions named to underscore string. To underscore string. Here we are using the to underscore string function defined in the toString trait, which the standard library has implemented for any type that implements display. We have another useful pattern that exploits the implementation details of Tuple Structs and Tuple Struct enumeration variants. These types use in parentheses as initializer syntax, which looks like a function call. The initializers are usually implemented as functions returning an instance that's constructed from their arguments. We can use these initializers functions as function pointers that implement the closure traits, which means we can specify the initializer function as arguments for the methods that take closures like so. Here we create status : value instances using each U32 value in the range that map is called on by using the initializer function of status : value. Some people prefer this style and some people prefer to use closures. They compile to the same code, so use whichever style is clearer to you. Returning closures. Closures are represented by traits, which means you can't return closures directly. In most cases where you might want to return a trait, you can instead use a concrete type that implements the trait as a return value of the function. But you can't do that with closures because they don't have a concrete type that is returnable. You're not allowed to use the function pointer fn as a return type. For example, the following code tries to return a closure directly, but it won't compile. The compiler error is as follows. The error references the sized trait again. Rust doesn't know how much space it will need to store the closure. We saw a solution to this problem earlier. We can use a trait object. This code will compile just fine. For more about trait objects, refer to the section Using Trait Objects that allow for values of different types in Chapter 17. Next, let's look at macros. Macros. We've used macros like print, line, exclamation mark throughout this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust. Declarative macros with macro underscore rules exclamation mark, and three kinds of procedural macros: custom, hashtag, square bracket derived, square bracket macros that specify code within the derived attribute, used on structs and enumerations, attribute-like macros that define custom attributes unused on any item, function-like macros that look like function calls but operate on the tokens specified as their arguments. We've talked about each of these in turn, but first let's look at why we even need macros when we already have functions. The difference between macros and functions. Fundamentally, macros are a way of writing code that writes other code, which is known as metaprogramming. Okay, in Appendix C, we discussed the derived attribute, which generates an implementation of various traits for you. We've also used the print line exclamation mark and the vec exclamation mark macros throughout the book. All of these macros expand to produce more code than the code you've written manually. Macro media programming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. However, macros have some additional powers that functions don't. A function signature must declare the number and the type of parameters the function has. Macros, on the other hand, can take a variable number of parameters. We can also call print line exclamation mark hello with one argument, or print line exclamation mark hello curly brackets name with two arguments. Also, macros are expanded before the compiler interprets the meaning of the code. So a macro can, for example, implement a trait on a given type. A function can't, because it gets called at runtime and a trait needs to be implemented at compile time. The downside to implementing a macro instead of a function is that a macro definitions are more complex than function definitions because you're writing Rust code that writes Rust code. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain than function definitions. Another important difference between macros and functions is that you must define macros or bring them into scope before you can call them in a file. As opposed to functions, you can define anywhere and call anytime. Declarative macros with macro underscore rules exclamation mark for general metaprogramming. The most widely used form of macros in Rust is declarative macros. These are also sometimes referred to as macros by example, macro underscore rules exclamation mark macros, or just plain macros. At their core, declarative macros allow you to write something similar to a Rust match expression. As discussed in Chapter 6, match expressions are control structures that take an expression, compare the resulting values of the expression to patterns, and then run the code associated with the matching pattern. Macros also compare a value to patterns that are associated with particular code. In this situation, a value is the literal Rust source code passed to the macro. The patterns are compared with the structure of the source code and the code associated with each pattern. When matched, replaces the code passed to the macro. This all happens during compilation. To define a macro, you use the macro underscore rules exclamation mark construct. Let's explore how to use macro underscore rules exclamation mark by looking at how the vec exclamation mark is defined. In Chapter 8 covered how we can use the vec exclamation mark macro to create a new vector with particular values. For example, the following macro creates a new vector containing 3 integers. We could also use the vec exclamation mark macro to make a vector of 2 integers or a vector of 5 string slices. We wouldn't be able to use a function to do the same because we wouldn't know the number of type of values up front. Listing 19-28 shows a slightly simplified definition of the vector exclamation mark macro. Listing 19-28, a simplified version of the vec exclamation mark macro definition. Note the actual definition of the vec exclamation mark macro in the standard library includes code to pre-allocate the correct amount of memory up front. The code is then optimized that we don't need. The code is an optimization that we don't include here to make the example simpler. The hashtag close quote macro underscore export close quote close bracket square bracket macro underscore export square bracket annotation indicates that this macro should be made available whenever the crate in which the macro is defined is brought into scope. Without this annotation, the macro can't be brought into scope. We then start the macro definition with macro underscore rules exclamation mark and the name of the macro we're defining without the exclamation mark. The name, in this case vec, is followed by curly brackets denoting the body of the macro definition. The structure in the vec exclamation mark body is similar to the structure of a match expression. Here we have one arm with the pattern, and that is going to be, oh boy, parenthesis, $parenthesis, $x colon expr, parenthesis, comma, what do we call that? Call that an asterisk. parenthesis, followed by equals, greater than, and the block of code associated with this pattern. If the pattern matches, the associated block of code will be emitted. Given that this is the only pattern in this macro, there is only one valid way to match. Any other pattern will result in an error. More complex macros will have more than one arm. Valid pattern syntax in macro definitions is different than pattern syntax covered in Chapter 18 because macro patterns are matched against Rust code structure rather than values. Let's walk through what the pattern pieces in listing 19-28 mean. For the full macro pattern syntax, see the references. First, a set of parentheses encompasses the whole pattern. A $sign is next, followed by a set of parentheses that captures values that match the pattern within the parentheses for use in the replacement code. Within the $sign parentheses is the $X of course, I've got to look at my cheat sheet. $X colon X EXPR, which matches any Rust expression. EXPR expression. And gives the expression name $X. The comma following the $sign parentheses indicates that the literal comma separator character could optionally appear after the code that matches the code in the $sign parentheses. The asterisk specifies that the pattern matches 0 or more of whatever precedes the asterisk. When we call this macro with the vector exclamation mark, close brackets, 1, 2, 3, close brackets, semicolon, the $X pattern matches 3 times with the 3 expressions 1, 2, and 3. Now, let's look at the pattern in the body of the code associated with this arm. Temp underscore vec dot push parentheses. Within the $sign parentheses, and why does that always give me so much trouble? And of course, I know asterisk. Yeah. Okay. Well, 1, 2, 3. Now let's look at the pattern in the body of the code associated with this arm. Temp underscore vec dot push parentheses within the $sign parentheses asterisk is generated for each part that matches $sign parentheses in the pattern 0 or more times depending upon how many times the pattern matches. The $sign X replaced each expression matched. When we call this macro with vector exclamation mark, close bracket, 1, 2, 3, close bracket, semicolon, the code generated that replaces this macro call will be the following. We've defined a macro that can take any number of arguments of any type and can generate code to create a vector containing the specified elements. There are some strange edge cases with macro underscore rules exclamation mark. In the future, Rust will have a second kind of declaration macro that will work in a similar fashion but fix some of these edge cases. After that update, macro underscore rules exclamation mark will be effectively deprecated. With this in mind, as well as the fact that most Rust programmers will use macros more than write macros, we won't discuss macro underscore rules exclamation mark any further. To learn more about how to write macros, consult the online documentation or other resources such as the Little Book of Rust Macros. Procedural macros for generating code from attributes. The second form of macro is procedural macros, which act more like functions and are a type of procedure. Procedural macros accept some code as an input, operate on that code, and produce some code as an output rather than matching against patterns and replacing the code with other code as declarative macros do. The three kinds of procedural macros, custom derived, derive, attribute-like, and function-like, all work in a similar fashion. When creating procedural macros, the definition must reside in their own crate with a special crate type. This is for complex technical reasons that we hope to eliminate in the future. Using procedural macros like the code in listing 19-29, where some underscore attribute is a placeholder for using a specific macro. Listing 19-29, an example of using a procedural macro. The function that defines a procedural macro takes a token stream as an input and produces a token stream as an output. The token stream type is defined by the procedure, I'm guessing procedure underscore macro crate that is included with Rust and represents a sequence of tokens. This is the core of the macro. The source code that the macro is operating on makes up the input token stream, and the code the macro produces is the output token stream. The function also has the attribute attached to it that specifies which kind of procedural macro we're creating. We can have multiple kinds of procedural macros in the same crate. Let's look at the different kinds of procedural macros. We'll start with a custom derive macro and then explain the small dissimilarities that make the other forms different. How to write a custom derive macro. Let's create a crate named hello underscore macro that defines a trait named hello macro with one associated function named hello underscore macro. Rather than making our crate users implement the hello macro trait for each of their types, we'll provide a procedural macro so users can annotate their type with hashtag close bracket derive parenthesis hello macro parenthesis close bracket to get a default implementation of the hello underscore macro function. The default implementation will provide hello macro exclamation mark my name is type name exclamation mark, where type name is the name of the type on which the trait has been defined. In other words, we'll create a crate that enables another programmer to write code like listing 19-30 using our crate. Listing 19-30, a code a user of our crate will be able to write when using a procedural macro. This code will print hello macro exclamation mark my name is pancakes exclamation mark. When we're done, the first step is to make a new library crate like this. Next, we'll define the hello macro trait and its associated function. We have a trait and its function. At this point, our crate user would implement the trait to achieve the desired functionality like so. However, they would need to write an implementation block for each type that they wanted to use with hello underscore macro. We want to spare them from having to do this work. Additionally, we can't yet provide the hello underscore macro function with default implementation that will print the name of the type of trait type the trait is implemented on. Rust doesn't have reflection capabilities, so it can't look up the type's name at runtime. We need a macro to generate code at compile time. Capabilities, reflection capabilities. Okay, the next step is to define the procedural macro. At the time of this writing, procedural macros need to be in their own crate. Eventually, this restriction might be lifted. The convention for structuring crates and macro crates is as follows. For a crate name foo, a custom derive procedural macro crate is called foo underscore derive. Let's start a new crate called hello underscore macro underscore derive inside our hello underscore macro project. Our two crates are tightly related, so we create the procedural macro create crate within the directory of our hello underscore macro crate. If we change the trait definition in hello underscore macro, we'll have to change the implementation of the procedural macro in hello underscore macro underscore derive as well. The two crates will need to be published separately, and programmers using these crates will need to add both as dependencies and bring them both into scope. We could instead have the hello underscore macro crate use hello underscore macro underscore derive as a dependency and re-export the procedural macro code. However, the way we've structured the project makes it possible for programmers to use hello underscore macro even if they don't want the derive functionality. We need to declare the hello underscore macro underscore derive crate as a procedural macro crate. We'll also need functionality from the syntax, syn, and quote crates, as you'll see in a moment. So we need to add them as dependencies. Add the following to the cargo toml file for hello underscore macro underscore derive. To start defining the procedural macro, place the code in listing 1931 into your source library source/libraries.rs file for the hello underscore macro underscore derive crate. Note that this code won't compile until we add definitions for the implement underscore hello underscore macro function. Listing 19-31 code that most procedural macro crates will require in order to process Rust code. Notice that we've split the code into the hello underscore macro underscore derive function, which is responsible for parsing the token stream, and the implement underscore hello underscore macro function, which is responsible for transforming the syntax tree. This makes writing the procedural macro more convenient. The code in the outer function parenthesis hello underscore macro underscore derive, in this case parenthesis, will be the same for almost every procedural macro crate you see or crate. The code you specify in the body of the inner function implement underscore hello underscore macro in this case will be different depending on your procedural macro's purpose. We've introduced three new crates: PROC procedural underscore macro syntax syn and quote. I'm guessing that's procedural. PROS, I don't know, maybe process underscore macro crate comes with Rust, so we didn't need to add that to the dependencies in cargo.toml. The PROC underscore macro crate is the compiler's API that allows us to read and manipulate Rust code from our code. The sync, I think that's sync, syn, crate parses Rust code from a string into a data structure that we can perform operations on. The quote crate returns .syn data structures back to the Rust code. These crates make it much simpler to parse any sort of Rust code we might want to handle. Writing a full parser for Rust code is no simple task. Okay, the hello underscore macro underscore derive function will be called when a user of our library specifies hashtag close bracket derive parenthesis hello macro parenthesis close bracket on a type. This is possible because we've annotated the hello underscore macro underscore derive function here with the proc underscore macro underscore derive and specified the name hello macro, which matches our trait name. This is the convention most procedural macros follow. The hello underscore macro underscore derive function first converts the input from a token stream to a data structure that we can have, interpret, and perform operations on. This is where syntax, SYN, comes into play. I think that's syntax. The parse function in SYN takes a token stream and returns a derive input struct representing the parse Rust code. Listing 19-32 shows the relevant parts of the derive input struct that we get from parsing the struct pancake string. Listing 19-32, the derive input instance we get when parsing the code that has the macros attribute in listing 19-30. The fields of the struct show that the Rust code we've parsed is a unit struct with the IDENT, must be identifier. Identifier meaning the name of pancakes. There are more fields on this struct for describing all sorts of Rust code. Check the SYN documentation for derive input for more information. Soon we'll define the implement underscore hello underscore macro function, which is where we'll build the new Rust code we want to include. But before we do, note that the output for the derive macro is also a token stream. The return token stream is added to the code that our crate users write. So when they compile their crate, they'll get an extra functionality that we provide in the modified token stream. You might have noticed that we're calling unwrap to cause the hello underscore macro underscore derive function to panic if the call to the SYN : parse function fails here. It's necessary for our procedural macro to panic on errors because PROC, what did we say that was? Procedural underscore macro underscore derive functions must return token stream rather than result to conform to the procedural macro API. We've simplified this example by using unwrap in production code. You should provide more specific error messages about what went wrong by using panic, ! or expect. Okay, now that we have the code to turn the annotated Rust code from a token stream into a derive input instance, let's generate the code that implements the hello macro trait on the annotated type as shown in listing 19-33. Listing 19-33, implementing the hello macro trait into, using the parsed Rust code. We get an indent struct instance containing the name identifier. I've got to try to remember that IDENT stands for identifier. Struct instance containing the name identifier in the annotated type using assist.identifier. The struct in listing 19-32 shows that when we run the implementation underscore hello underscore macro function on the code in listing 19-30, the identifier we get will have the identifier field with the value of pancakes. Thus, the name variable in listing 19-33 will contain an identifier struct instance that when printed will be the string pancakes, the name of the struct in listing 19-30. The quote exclamation mark macro lets us define the Rust code that we want to return. The compiler expects something different to the direct result of the quote exclamation mark macro execution. So we need to convert it to a token stream. We do this by calling the into method, which consumes this intermediate representation and returns a value of the required token stream type. The quote exclamation mark macro also provides some very cool templating mechanics. We can enter a hashtag name and quote exclamation mark will replace it with the value in the variable name. You can even do some repetition similar to the way regular macros work. Check out the quote crates doc for a thorough introduction. We want our procedural macro to generate an implementation of our hello macro trait for the type the user annotated, which we can get by using hashtag name. The trait implementation has one function, hello underscore macro, whose body contains the functionality we want to provide, printing hello, comma, macro, exclamation mark, my name is, and the name of the annotated type. The stringify exclamation mark macro used here is built into Rust. It takes a Rust expression such as 1 plus 2 and at compile time turns the expression into a string literal such as 1 plus 2. This is different than format exclamation mark or print line exclamation mark macros, which evaluate the expression and then return the result to a string. There is a possibility that the hashtag name input might be an expression to print literally, so we use stringify exclamation mark using stringify also saves an allocation by converting hashtag name to a string literal at compile time. At this point, cargo build should complete successfully in both hello underscore macro and the hello underscore macro underscore derive. Let's hook up these crates to the code in listing 19-30 to see the procedural macro in action. Create a new binary project in your projects directory using cargo new pancakes. We need to add hello underscore macro and the hello underscore macro underscore derive as dependencies in the pancakes crates cargo taml. If you're publishing your version of hello underscore macro and the hello underscore macro derive to crates.io, they would be regular dependencies. If not, you can specify them as path dependencies as follows. Put the code in listing 19-30 into source/main.rs and run the cargo run. It should print hello macro exclamation mark my name is pancakes. The implementation of the hello macro trait from the procedural macro was included without the pancake trait needing to implement it. The hashtag close bracket derive parenthesis hello macro parenthesis close bracket added the trait implementation. Next, let's explore how other kinds of procedural macros differ from custom derived macros. Attribute-like macros. Attribute-like macros are similar to custom Derive macros, but instead of generating code for the Derive attribute, they allow you to create new attributes. Okay, they're also more flexible. Derive only works with structs and enumerations. Attributes can be applied to other items as well, such as functions. Here's an example of using an attribute like macros. Say you have an attribute named route that annotates functions when using a web application framework. This hashtag route, a close bracket route, close bracket attribute would be defined by the framework as a procedural macro. The signature of the macro definition function would look like this. Here we have two parameters of type tokenstream. The first is the contents of the attribute, the get, comma, double quote, forward slash double quote part. The second is the body of the item the attribute is attached to. In this case, fn, index, parentheses, squiggly bracket, and the rest of the function's body. Other than that, attribute-like macros work the same as custom Derive macros. You create a crate with the proc-macro crate type and implement a function that generates the code you want. Function-like macros. Function-like macros define macros that look like function calls, similarly to macro underscore rules exclamation mark macros. They're more flexible than functions. For example, they can take an unknown number of arguments. However, macro underscore rules exclamation mark macros can be defined only using match-like syntax we discussed in section Declarative Macros with macro underscore rules exclamation mark for general meta programming. Earlier, function-like macros take a token stream parameter and their definition manipulates that token stream using Rust code as the other two types of procedural macros do. An example of a function-like macro is SQL exclamation mark macro that might be called like so. SQL. This macro would parse the SQL statement inside and check that it's syntactically correct, which is much more complex processing than a macro underscore rules exclamation mark macro can do. The SQL exclamation mark macro would be defined like this. The definition is similar to custom Derive macros signature. We receive the tokens that are inside the parentheses and return the code we want to generate. Summary. Now that you have some Rust features in your toolbox that you won't use often, but you'll know they're available in very particular circumstances, we've introduced several complex topics so that when you encounter them in error message, suggestions, or in other people's code, you'll be able to recognize these concepts and syntax. Use this chapter as a reference to guide you to solutions. Next, we'll put everything we've discussed throughout the book into practice into one more project. Well, that completes chapter 19. For the very last chapter, chapter 20, that will be in the next video. So hope to see you there.